Today we're going to be taking a look at what is probably, well, all the rules are important, but this is arguably one of the most important rules for taking derivatives, one of the most useful, one that comes up all over the place, and just one that without it, everything would be much, much harder. So let me tell you what this rule is called. This rule is called the chain rule. And what is the chain rule? So the question we want to start asking ourselves, we now know how to take derivatives of a lot of different functions. We know how to take derivatives of polynomials. We know how to take derivatives of rational functions. We know how to take derivatives that involve things like square roots, although we haven't yet proved why that works. Today we're going to be able to do that by using the chain rule. We know how to take derivatives of things like e to the x. We know how to take derivatives of trig functions. And we know how to take derivatives of combinations of functions that involve addition, subtraction, multiplication, and division. But that leaves out one of the most important ways that you can build new functions out of old ones, and that is composition. So today we're going to start looking at what do you do if you have two functions composed together. Now, in other words, we're asking ourselves what happens if you are taking the derivative of f of g of x. In other words, f composed with g. And supposing here that g is differentiable at x, and we don't want to say that f is differentiable at x. That's not the interesting, or that's not the relevant point here. The relevant point that we're going to want to look at is f prime at g of x exists. In other words, we need the derivative of f to exist, but not at x itself, because f isn't being evaluated at x or near x necessarily. F is being evaluated around g of x. So this is the condition that we want to think about. G prime exists at x, but f prime exists at g of x. Now, supposing that this is true, what can we say? Well, it's going to become a little bit tricky here at a certain point, but I'll tell you about the sort of technical issue that we run into when we get there. And apart from that one technical issue, things aren't going to be super bad, okay? There's a little bit of a trick still, but it's not too bad. But let's just write down what this is. This is the limit as h goes to 0 of f of g of x plus h minus f of g of x divided by h. And now, here is what I would like to do. I would like to say, and unfortunately I'm going to have to erase some stuff here. I would like to do the following kind of idea. I would like to say, well, suppose that we think about g of x as kind of a variable in its own right. We can sort of think of a new variable u that is equal to g of x. And then what I'd like to do is to write this. I would like to say that this is equal to the limit as h goes to 0 of, I'd like to multiply on the top and the bottom by a particular factor. And let me show you what that is. So I would like to say we have f of g of x plus h minus f of g of x. And then I'd like to multiply on the bottom by g of x plus h minus g of x. And on the top by g of x plus h minus g of x. And that leaves me with an h on the bottom. Now, I can do this provided that I'm not multiplying and dividing by 0. So in other words, as long as this term here isn't 0, what I just did is perfectly legal. The problem is that this could be 0. However, if g of x plus h is equal to 0, then this entire term is equal to 0. So I can fix this problem, and this This is the trick. Multiplying on the top and the bottom by g of x plus h minus g of x is the trick. The technical difficulty is that this could mean I'm multiplying on the top and the bottom by 0. Now, if for small h's, in other words, if for sufficiently small h, this term is never 0, well, then I don't have to worry about this. Then I can just do this and everything works out nicely. But maybe for sufficiently small h, maybe there is no choice where we can say, well, as long as we restrict h to being this small, we can guarantee that this denominator will not be 0. So what do we do then? Well, in that case, what we can do is we can say, let's replace this with a piecewise defined function, and it will be equal to this piece when g of x plus h is not equal to g of x. And then it will be equal to 0 when g of x plus h is equal to g of x. Now that's fine, because if g of x plus h is equal to g of x, then this whole thing is actually equal to 0 anyway. So now what we can do is we can say, well, what is happening here? This term here in the limit as h goes to 0 becomes g prime of x. And what is this big mess over here on the left? That's a little bit confusing. But think about g of x as a variable in its own right. Then this is really, because g is differentiable, it's also continuous. So as h goes to 0, g of x plus h minus g of x goes to 0. And in fact, this is just the derivative of f evaluated at g of x. Again, just think about this as a new variable and think about what happens in the limit as that variable goes to 0. Well, this is literally just f of b minus f of a divided by b minus a. And so in the limit, this is the derivative, except it's evaluated at g of x instead of at g. So as long as we don't have to worry about g of x plus h equals g of x, then this is just going to come out to be f prime evaluated at g of x times g prime of x. But what about in the cases where we do have to worry about that? Well, here's the nice thing. Suppose that no matter how small we consider h, there is a value of h smaller than that where this denominator would be 0, so that we have to just insert 0 into this limit. In that case, that means that this limit has to go to 0, because it means that this numerator can always be made 0, no matter how small we take our region around h equals 0, this numerator will still be 0. But this limit exists. So if that is a problem, then this limit also has to be going to 0. And this expression here is bounded. So we have something that is bounded times something that is 0. And in that case, that limit is going to be 0. So this is going to either come out to be f prime of g of x times g prime of x, or it's going to be 0 and g prime of x is equal to 0. However, in that case, we can just consolidate this all down into 1 and say, well, what that really means is it's always f prime of g of x times g prime of x. So there we go. We've worked out this nice little formula for what is the derivative of the composition of functions. Now, the technical issue there, that is a really confusing sort of thing. And so I don't expect everybody to necessarily follow that argument the first time you see it. And I don't expect you in this course to be able to make that argument. But I do recommend that you think about this, watch a couple of times and try to understand it, because it is a useful trick. And if you understand it, then you know that you really understand limits and things like that. There's a second, maybe slightly more intuitive way of thinking about this, because you can kind of think of the whole thing as the limit as delta x goes to 0 of the change in f composed with g divided by the change in x. And we can sort of think of this as the limit as delta x goes to 0 of the change in f per change in g times the change in g per change in x. Again, provided that the change in g is not 0. So let me note that down here. We have delta g not equal to 0. And then this sort of leads us to say, oh, yes, so this is the idea where there's another notation for this where we can say this is the derivative of f with respect to g times the derivative of g with respect to x. So some people like to write the chain rule this way. I personally prefer to write it this way. And the reason is because this way reminds me that I'm really taking f prime and then evaluating it at g of x. I'm not simply taking the derivative of f with respect to g. I mean, I am, but then I'm evaluating it at g rather than just plugging in x, if that makes sense. So to me, the fact that you don't have information on what to plug in here makes this notation not incorrect, but it doesn't remind me of what to do next the way that this notation does. So let's take a look at some examples of doing this kind of thing, because that's really what we're going to be focusing on mostly here from here on out. We're not going to worry so much about the proof of this, although, again, intuitively, it's not too difficult to see what's going on here, because as long as the change in g, as long as g is not constant near x, or as long as g doesn't like fluctuate back and forth and hit 0, in other words, as long as the secant lines are all non-zero slope near x, what we can do is we can say, well, in that case, we're really just observing that you can replace change in f per change in x with change in f per change in g times change in g per change in x. So we're really just doing the derivative of f evaluated at g of x times g prime of x. And then all of those technical details are to worry about the case where everything comes out to be 0 at the end anyway. It's kind of a weird thing. It's like 90% of the work is to show that something happens to be 0 in a special case. Well, maybe not 99, maybe not 90%, but like a substantial part of the technical issue just comes into play where we have to worry about the possibility that something could go wrong, but it turns out it's always 0 in that case. So yeah, kind of an interesting situation there. Anyway, let's look at some examples. Let's suppose that I want to take the derivative of, let's say, e to the x squared. Well, here's what I want to think about here. This is going to be, my f of x is going to be e to the x, and my g of x is going to be x squared. Because if I write it this way, then f composed with g of x is e to the x squared. Now, if I do that, then f prime of x is still e to the x, and g prime of x is going to be 2x. So, my derivative is f prime evaluated at g. So that's still e to the x squared, and then it is multiplied by a 2x. And traditionally, we would write the 2x in front just because it makes it easier to read. It doesn't, like in this case, sometimes if your handwriting is sloppy or something, it's kind of easy to think, oh, maybe the 2x is in the exponent or something. So putting it out front avoids us misreading things. It's just, you don't have to. It's not like a mathematical rule, but it's sort of a convention that just makes things a little simpler to read if everybody follows the same convention. So there's one example. Here's another example of this kind of thing. Let's suppose that we have the derivative of, and this is going to be one that we could actually do without the chain rule too if we wanted to. So I will give you a chance to do that if you would like. Let's suppose that I have 3x squared minus x raised to the 8th, and I want to take the derivative of that. Now, I could absolutely go through and raise this to the 8th. I could go use the binomial theorem, expand this into some massive polynomial, and do it that way. But the chain rule is going to give me a super fast way to do this that avoids me having to write a polynomial that would spread halfway across the wall here. So how would I do this with the chain rule? Well, let me actually give you a minute. Can you think of how I could break this down into two simple functions that are composed together and then apply the chain rule? Take a moment to think about that and then come back and we'll see if we got the same thing. Okay, so the way that I would do this is I think of my outer function f as x to the 8th because I see here that the last operation I do is I raise something to the 8th power. And the inner function here is going to be the 3x squared minus x. Now, one of the reasons that's nice is because that's a reasonably easy function to deal with. There's no, like that's an easy thing to take the derivative of. It's just a tiny little polynomial. We're good with those kinds of things, hopefully, by this point. If you're not, make sure to go back and refresh yourself on how to take these kinds of derivatives. But hopefully you're okay with this kind of thing at this point. So then I can say, well, f prime is going to be 8x to the 7th. Because I know how to take the derivatives of things like, powers like that. That's just straightforward. You take 8x to the 7th and you're done. And then g prime is going to be 6x minus 1. Again, that's pretty straightforward to do, hopefully at this point. And now we just have to put this together. So f prime evaluated on g, that's going to be 8 times 3x squared minus x raised to the 7th power. And then I have to multiply by g prime, which is going to be 6x minus 1. So I've got this answer here, and the nice thing is that I was able to do this without having to appeal to any complicated algebra stuff. Like, again, I could have done this by expanding it out, but that would be a lot of work. It would be very easy to make a mistake, and it would just take up a tremendous amount of space. And then at the end, it wouldn't necessarily be obvious how that resulting thing factors. As it turns out, being able to factor the derivatives is a nice thing to be able to do. And if I take the derivative with the chain rule, oh look, it's pre-factored for my convenience. Well, except for the 3x squared minus x. I can factor this a bit further if I wanted to, but it's mostly all factored for me. So there's a lot of advantages to doing this with the chain rule, even though we don't have to. Now, that first example that I showed you, you had to do that with the chain rule. I don't think there's any way of doing that other than using the chain rule. So let's take a look at another example where, again, you must use the chain rule. Let's suppose that I want to take the derivative of the tangent of x cubed. Well, what I'm going to do in this case is I'm going to take f of x to be equal to tangent x, which would make my f prime of x into secant squared x. Hopefully everybody remembers that from last time. That's one of the rules we figured out for taking derivatives of trig functions. And if you don't remember that, you can always get it back by using the quotient rule on sine x over cosine x. Then I will take g of x to be equal to x cubed, which makes g prime of x 3x squared. So again, that's just a nice little power rule application there, nothing too bad. So this is going to become secant squared of g, which is x cubed, multiplied by 3x squared. And kind of like we did with that exponential example, we tend to put 3x squared in front and then the secant squared of x cubed after that. Again, this is just a convention that we usually put it in this order. It's not like it's mathematically required or anything like that. So there we go. A nice little example there of taking this derivative. Now, of course, sometimes we want to take higher order derivatives or do other things where we use the chain rule together with other rules. So let's suppose that I want to find the second derivative of, what do I want to do here? Let's suppose that I want to do the sine of e to the x. Well, what I'm going to do is I'm going to start by finding the derivative. Obviously, to find a second derivative, we have to find the first derivative first, generally speaking. Maybe there's some exception where you can just see the second derivative immediately, but usually you're going to have to find the first derivative first. So to do this, I'm going to take as my outer function f of x equals sine x. That means that f prime is going to be cosine x. Again, look back to our lecture on the trig function stuff, and we worked this out by using a neat little geometric argument. Then my g of x is going to be equal to e to the x. That makes g prime of x equal to e to the x as well. So this is going to become cosine of g of x, so cosine of e to the x times e to the x. So now what we're going to do is we're going to try to find the derivative of this expression, because I'm really trying to find the second derivative. This is the first derivative, so we've got to keep on going and find the second derivative. And take a moment, if you have any confusion about this, go back and think about where we got this, because now we're going to be just moving on to this, and I have to erase some stuff to make some space. So I'm going to put the exponential first, no particular reason, just, again, that's kind of the convention. And let's think about this one. Well, in order to do this, I need to use the product rule, because this is a product of e to the x with cosine e to the x. So for my product rule, I can say f equals e to the x. That means f prime equals e to the x. And g is equal to cosine e to the x. Now, how do I find g prime? Well, I need to apply the chain rule. So in this case, the outer function is cosine and the inner function is e to the x. The derivative of that inner function is still going to be e to the x. The derivative of the outer function is negative sine. Let me give myself a bit more space. So that picks up a negative sign. And then we have sine composed with the original function inside, which was e to the x. So we get negative e to the x times the sine of e to the x. By the way, this is where saying things out loud in English can get a little confusing, because sine versus sine, S-I-G-N versus S-I-N-E, they sound exactly alike. You probably have encountered this confusion before. So hopefully from context it's clear what's going on and from what I write, but do be aware that, yeah, it can sound confusing if you're just listening to somebody talk, because you don't know if they're talking about positive versus negative, S-I-G-N, versus trigonometry, sine, S-I-N-E. There's also, and this is totally unrelated to math, but I believe historically the English word sine, S-I-G-N, was pronounced ziggin. The silent G was actually pronounced. Unfortunately, English had the misfortune that the written form of English was established a really long time ago, or standardized a really long time ago compared to a lot of other languages. And as a result, it got standardized kind of with old-fashioned spellings that the pronunciations changed afterwards. So it's really a fascinating story. If you go look it up, there's not just things like dropping this, this silent G thing. There's also things like the great vowel shift. So a lot of words, if you look at, say, a Shakespearean play or poem, you look at some things and you're like, that doesn't rhyme. Why did he do this? This doesn't make any sense. Well, it rhymed at the time, but our pronunciation of the words has changed in the intervening 400, 500 years. I can't count off the top of my head how long it's been. The point is that, one of the reasons English spelling is so screwy is because our pronunciations changed, and the spelling used to make sense, and it used to be pronounced phonetically, but then people changed how they pronounced the word, and they didn't bother to change the spellings. The other reason our spelling is screwy is because English has the misfortune of being a Germanic language where half our vocabulary comes from the Romance languages. And thus we have these conflicting spellings that happen. And again, history of languages is really interesting stuff, but let's get back to this problem in math. So, if you remember, before we went off on a tangent there, not a tangent line, but a tangent, we were trying to take this derivative, and this is our stuff for the product rule. And so now I just have to put this together. F prime times g, that's e to the x cosine e to the x, plus fg prime, which is going to be negative e to the x sine e to the x, and I can factor one copy of e to the x out here and write this as e to the x cosine e to the x minus e to the x sine e to the x. And there we go. Okay, so this might seem kind of complicated, and it is a bunch of different steps, but here's the nice thing. Every single step is very much fixed by the problem itself. There's not a whole lot of choice involved in what to do next. We took our first derivative, and the only thing we could really do was a chain rule. Then we ended up with this expression, e to the x cosine e to the x, and we wanted to take the second derivative, so we're differentiating this. Well, really, the obvious thing to do is to break this into a product, and then within this product, we had to use the chain rule again, but, that's no trouble, that we just do. And then we just plug those results back into the product rule and simplify the resulting expression a bit. So, it's many steps, but each step, there's sort of, you look at it and ask yourself, well, what is the only rule that applies here? And there will only be one rule that applies in pretty much most circumstances, and you just use it, and you'll get where you're going. So this is the nice thing about taking derivatives. We have a few different rules that you have to memorize, but usually it's pretty obvious which rule to use next. Now, it's not necessarily obvious when you first start. It can take some time to get used to them, but once you are used to the rules, then it sort of becomes, oh, yes, there's really only one rule that applies here. So at first, it doesn't look obvious. I shouldn't say it's obvious right off the bat, but once you get used to everything, then it sort of becomes a very automatic procedure almost. There's like this, okay, this is the rule that I see applies, use the rule, now what rules seem to apply, and we just keep on working our way through like that. All right, so let's take a look now at some special cases of the chain rule. Well, really one particular special case of the chain rule that I want to observe because it's important enough that we tend to kind of memorize it separately as a special case of the chain rule. So, well, there's really two different special cases of the chain rule that we want to look at. The first one is going to be the derivatives of e raised to the g of x. In this case, my f of x is equal to e to the x, and my g of x is just g of x. F prime of x is also e to the x in this case. So what does this come out to be? Well, it's going to come out to be g prime of x times e to the g of x. In other words, to take this derivative, I just take the derivative of the exponent and multiply by it. You don't have to memorize this separately. This is just what you get when you use the chain rule. However, a lot of people like to remember this separately because taking derivatives of exponentials comes up an awful lot, and it's a fairly straightforward rule to remember. You literally just multiply by the derivative of the exponent. But a word of caution, do not get this confused with the power rule, okay? These are different things. Don't try to do something like, and this is something else that I see people do. They think, oh, if I take something like the derivative of e to the x, they'll write something like e to the x minus 1 or something. No, the exponent doesn't change. And this is a thing about derivatives of exponentials in general. So just remember, the exponents don't change when we're talking about exponentials. They only change if we're talking about constant powers of the variable. So the power rule and dealing with exponentials, totally different things, even though they both involve an exponential operation. One involves an exponential function and one involves a power function. The other special case of the chain rule that we want to think about is something called the generalized power rule. So how does the generalized power rule work? Well, suppose that I want to take the derivative of g of x raised to the nth power. Sorry, that does not look like an n. There we go. That's more like an n. What I can do here is I can take my outer function to be f of x is equal to x to the n. Then f prime of x is nx to the n minus 1. And g of x, just like in this case with the exponentials, g of x is some function. Who knows what function it is? But we're assuming here it's differentiable. So this is simply going to become n times g of x to the n minus 1 times g prime of x. So we do the power rule as usual, but then we have to multiply by the derivative of what's inside. Let's take a quick look at some examples of using these two rules just to kind of see how quickly we can do these kinds of things with them. So let's suppose that I want to do the derivative of e raised to the, let's do the cosine of x. Well, from that rule for exponential functions that I just wrote down, all I have to do is multiply by the derivative of cosine x. So that means I multiply by negative sine x, and then I still just have e to the cosine x. And there we go. I've got this thing written down immediately. So you can see how quick it is to work out like this. You really can go through this very, very fast. And to see an example with the generalized power rule, well, let's suppose that I have the derivative of, let's say, e to the x minus sine x raised to the 6th power. Now, once again, we could actually expand this thing out. That's the thing about the generalized power rule. You can often actually expand out whatever you've got on the inside and figure it out that way. But frankly, this is much, much easier. Well, this is going to be 6 times e to the x minus sine x raised to the 5th, and then I just have to multiply by the derivative of what's inside, which in this case is going to be e to the x minus cosine x. So there we go. We've got our answer very, very quickly here. So those two special cases are worth remembering as kind of, I don't like memorizing things, but these are special cases that come up so often, and the rules are so relatively straightforward that I do recommend memorizing these two special cases, not these particular problems, but the rule for exponents and the rule for the generalized power rule. Those are worth remembering as special cases of the chain rule. You can always get it back as a special case of the chain rule, though. So if you just remember the chain rule, yeah, you'll be all set. But it will save you some time if you memorize these special cases that come up so often. Now, one more thing I want to mention here, well, a couple more things before we finish with this. The first thing is that you can keep on going this way. So if I wanted to work out what is the derivative of f composed with g composed with h, well, this would be equal to f prime of g of h, sorry, h of x, let's say, g of h of x, times the derivative of what's inside, which is g composed with h of x. And then you just keep on going. So this is now f prime of g of h of x times g prime of h of x times h prime of x. So we can repeatedly use the chain rule on composition, and it just keeps on getting longer. And this is one reason why it's called the chain rule. I think of it as the chain rule because composition of functions is like chaining functions together. But you can also think of it as the chain rule because if you keep on chaining functions together, the chain rule just keeps on chaining together their derivatives like this. Another way that some people like to write this is that the derivative of f composed with G composed with H is dF by dG times dG by dH times dH by dx. So dF by dG is F prime evaluated at G. dG by dH is G prime evaluated at H. And then H prime is, of course, just dH by dx. Again, I'm not a big fan of this notation for the chain rule, but if you like it, then use it. Because it's about what makes things easy for you more than what makes it easy for me. I'm just telling you, I prefer to think of it in this way, but whatever makes the most sense to you, whatever makes it the easiest for you to use the rules, that's what I want you to do. Just make sure that what you're doing is really what you're supposed to be doing, okay? And as long as you're doing that, I don't care what method you use to remember it or anything like that. The second observation I want to make here is, well, okay, before I finish with this, I should say, we could keep on going, right? We could end up with 4 or 5 or 6 or 7 functions composed together. Well, you just keep on breaking it down, and you end up you continue to chain on more and more derivatives. So, the same process continues to work. So the next thing I want to observe, though, is that we can use all of these rules in any combination that we want to. And we've seen some of those examples today. Like when we took that second derivative, we ended up having to use a product rule together with the chain rule. Well, you have other problems where maybe you need to use a quotient rule and the chain rule. Or maybe you need to use several different rules in combination. Maybe you have something that's a product, something that's a quotient, and something that's a chain rule. So there's all kinds of different ways of, you just have to ask yourself, okay, how do I break this down into smaller pieces until we get down to pieces where we know the derivatives? That's kind of the key point. You used all the different rules, and you can use any rule as long as it applies to the expression you're trying to differentiate. You use any rule, and you break it down into simpler pieces until you get to where you just know what the derivative is, and then you put all those pieces back together. One more quick application of the chain rule that I want to show you is we never proved the quotient rule. And you can prove the quotient rule. Maybe I did prove the quotient rule. Now I don't remember if I proved the quotient rule for you or not. You can prove the quotient rule. Oh yeah, we did prove the quotient rule. But I want to show you a slick way of proving the quotient rule from the product rule and the chain rule. So quotient rule from product and chain rule. If I want to take the derivative of f of x divided by g of x, this is actually the derivative of f of x times g of x to the minus 1. This is going to be f prime times g of x to the minus 1 plus f of x times the derivative of g of x to the minus 1. But from the generalized power rule, this is going to be f prime. I'm going to drop the of x's because it's getting really tiring writing all of those out. F prime g to the minus 1. Actually, I'm going to leave the x's just because I've been using them so far. That way we don't have any confusion here. G of x to the minus 1. And then we're going to get minus f of x times g of x to the minus 2 times g prime of x. And we can rewrite this as, if I factor out a g of x to the minus 2, this becomes f prime of x, g of x, minus f of x, g prime of x, divided by g of x squared. So actually, once you prove the product rule and the chain rule, you get the quotient rule for free. So although we can prove the quotient rule by going back to the definition with a limit and playing around with it there, and I think I did actually do that for you in our lecture on the quotient rule, you don't really need to do that because you can get it just by doing the product rule and the chain rule. All right, so what we're going to do in our next lecture is we're going to kind of step back from new rules for a moment, and we're going to just take a look at several examples of derivatives and sort of recognizing how to use or how to know what rule you want to use. And after that, we'll start talking about some other techniques. But in the meantime, make sure to keep practicing and reading, and good luck. I'll see you soon.